Dear students, I am Mahesh Javalkar of Maratha Mandal Polytechnic, and today I am sending my sixth video on DCT questions for the subject BEEE, that is Basic Electrical and Electronics Engineering. So let's start with the question. Question number 101. So that is Lenz law of electromagnetic induction is as per law of conservation of what? Options are energy, momentum angular, charge, electromotive force. Okay. Now, whenever there is a changing magnetic flux, work done is there. Okay. Now, this changing magnetic flux work done is produced in induced EMF. Okay. So whenever there is a changing magnetic flux, a EMF is produced. That means one form of energy is being converted into another form of energy. Clear? That means Lenz's law of electromagnetic induction is as per law of conservation of energy. So here option A will be the right answer because energy is conserved. Okay. Then we'll go to the next question, question number 102. The current flows from A to B is as shown in the figure. The direction of the induced current in the loop is. Okay. Now here if you see the current which is flowing, here you can see the current which is flowing, it is in this direction. Okay. It is in this direction. Okay. Now the induced current, now this is the induced current what is shown, this is the induced current. Okay, induced current loop, induced current loop. Okay, now the direction of this induced current loop should be opposite to the direction of the current which has produced it. This is according to Lenz law. According to Lenz law, the induced EMF and the induced current will have a direction which opposes the very cause producing it. Okay, that means in this loop, the direction of current should be like this, like this. That means this should be like this. So this direction is opposite of this direction. Okay, so this direction you have to take. Now this direction if you see like this, it is nothing but a clockwise direction. It is a clockwise direction. So out of this option, the first option will be the right. Okay, so it is the induced current will be having clockwise direction. So as I have given in the explanation, by Lenz's law, the induced current must produce a inward flux to counter the magnetic flux of AB. So induced current is clockwise in the loop. That means the direction of induced quantity, whether it is current or EMF, will be just opposite to the very cause of induced current or voltage. The very cause of that, what is there, of that direction, it will be just opposite. Means if any current flowing through a conductor is inducing, okay, is inducing another current, okay, that induced current will have a direction opposite of the original current. This is according to Lenz's law. The direction has to oppose the very cause producing it. Okay, then we'll go to the next question. Question number 103. In a coil of self-induction of 5 henries, the rate of change of current is 2 amperes per second. Then EMF induced in the coil is. Okay. So here he has given L is equal to 5 henries. Okay. And the rate of change of current, that is di by dt. Okay. That is equal to 2 amperes per second. Okay. Now he has asked then EMF induced in the coil is what? Okay. Now induced EMF, okay, is given as minus L, okay, di by dt. Clear? Minus L by di by dt, because induced will be having the opposite direction, so that minus sign will come. Okay. So L is 5 and di by dt is 2. So minus 5 into 2, this is minus 10. So EMF is equal to minus 10. So answer will be minus 10. That is answer B over here will be the right answer. Okay. So here, this formula that EMF of a coil, okay, EMF induced in a coil is given as minus L di by dt. Okay, this formula we have to remember. So substituting the values in that formula, we get the answer as minus 10 volt, and minus 10 volt is the right answer over here. Clear? Then we'll go to the next question. Question number 104. Direction of current induced in a wire moving in a magnetic field is found by using which rule? Okay, so the rules what he has given is Fleming's left hand rule, Fleming's right hand rule, Ampere's rule, and right hand class rule. Okay, now out of this, direction of current induced in a wire moving in a magnetic field is given by Fleming's right hand rule. Okay, so this we have studied in our theory. So according to Fleming's right hand rule, we will get the direction of induced current in a wire which is moving in a magnetic field. So here answer should be answer B, Fleming's right hand rule. Okay. Then we'll go to the next question. Which of the following statements is not correct? Okay, so if you read the statements, option A, whenever the amount of magnetic flux linked with the circuit changes, an EMF is induced in the circuit. This is correct. Option B, the induced EMF lasts so long as the change in magnetic flux continues. This is also correct. Option C, the direction of induced EMF is given by Lenz law. That is also correct because Lenz law says that induced EMF or induced current will have a direction which is just opposite to the very cause producing it. Okay. Then D option says Lenz law is a consequence of the law of conservation of momentum. This statement is wrong because Lenz law is the law of conservation of energy, not momentum. Okay, so here option D is not correct. So option D is the answer. Lenz law is the consequence of the law of conservation of momentum. It is not momentum. The actual thing is energy. It is conservation of energy. Clear? Then we'll go to the next question. Question number 106. An inductor coil of inductance L is divided into two equal parts and both parts are connected in parallel, then what is the net inductance? Okay, so a L coil, we are having a L coil. This is inductance L coil. This will be divided into two. So you will be having this one coil and they will be connected in parallel. Okay, so you will be having another half coil here. So L is divided by 2 means this is L by 2 and this is also L by 2. Okay. Now L by 2, L by 2. Now they are connected in parallel. Now he is asking what is the net inductance. So net inductance, that is equivalent inductance in this case, will be parallel combination of inductance will give you the formula L by 2 into L by 2 upon L by 2 plus L by 2. Okay, so this is L square by 4 upon 2L by 2. Okay, so here 2 goes. Then what remains is L square upon 4 upon L. Okay, so this L goes, this square goes, it will come as L by 4. So L by 4 is the equivalent inductance for L by 2 inductors connected in parallel. Okay, so your option D will be the answer, L by 4. Okay, then we'll go to the next question, question number 107. The equivalent inductance between the points PQ in the figure is how much? Okay, so here we see we have three inductances. One inductance is 2H, another inductance is 4H, and another inductance is 2 by 3H. Okay, now these two are in parallel. These two are in parallel. 2H and 4H are in parallel. So if you take equivalent of that, it will be 2 into 4 upon 2 plus 4. Okay. This will be in series with 2 by 3. This will be in series with 2 by 3. Okay, so this is 8 upon 6 plus 2 by 3. Okay, this is equal to, if you take the LCM as 6, this will be 8 plus 2 into 2 is 4. So this is nothing but 12 upon 6. 6 1 the 6, 6 to the 12. So this is 2. So this will be 2 henries. Okay. So answer is 2 Henry about this equivalent circuit. So equivalent inductance between point P and Q will be 2 henries. So option A will be the right one, 2 henries. Okay. Then we'll go to the next question. Question number 108. Three inductors are connected as shown in the figure given below. What is its equivalent inductance? Again, same type of question is asked here. So here we see that zero point 0.5 Henry and another zero point 0.5 Henry are in parallel. Okay, and then this combination is in series with 0.75 Henry. Okay, so now here if you want to see this parallel combination, then equivalent of that parallel combination will be zero point 0.5 into zero point 0.5 upon zero point 0.5 plus zero point 0.5. This is in series with 0.75. Okay, now here 0.5 into zero point 0.5 is 0.25. So here you can take it as 0.25 upon 1 plus 0.75. So 0.25 plus 0.75 is nothing but 1. 1 Henry will be the answer over here. So option B will be the answer of 1 Henry. Okay. Then we'll go to the next question. An inductor works as a dash circuit for DC supply. Okay. Now, an inductor we know that is having a reactance. Reactance of inductance is given in the form of 2 pi FL. Okay. So 2 pi FL is the reactance of inductance. Now 2 pi FL, if it is reactance, then we can write this as XL is equal to 2 pi FL. Okay. Now for DC supply, F will be very, very less. F will be very, very less. That means 2 pi FL value will be less. So reactance will be less. Resistance to the flow of circuit will be very less. It is 0. Okay. So there will be no resistance for the current to flow. And when there is no resistance for the current to flow, then inductor should work as a short circuit. Then here, out of these options, option B will be the right answer. Because in the explanation also I have told you, the induced voltage across an inductor is 0 if the current flowing through it is constant. That is, inductor works as a short circuit for DC supply. So here, option B will be the right answer, short circuit. An inductor works as short circuit for DC supply. So we generally know that inductor passes DC, blocks AC, whereas a capacitor passes AC, blocks DC. This is a general statement. But what actually happens in that is about the reactance of inductance and capacitance. Now here for DC, that is when the frequency is less, frequency is almost 0, the reactance of inductor is very less. It is 0. Once the reactance is less, that means resistance to the flow of current is less. And once the resistance to the flow of current is less, that means that circuit is a short circuit. Clear? That means here option B is the right answer. Clear? Then we'll go to the next question. Two 10 Henry's inductors are in parallel. Okay. Two 10 Henry inductors are in parallel, and the parallel combination is in series with third 10 Henry inductor. What is the approximate total reactance when a voltage with frequency of 7 kilohertz is applied across the circuit? Okay. So first we will see what is the L equivalent. So first we will see here what is the L equivalent. So L equivalent says that two 10 Henry inductors are in parallel. That means 10 into 10 upon 10 plus 10. This is a parallel combination of two 10 Henry inductors. This is in series with 10 Henry. Okay. So this will come as 100 upon 20 plus 10. This will come as 25 times 5 plus 10. So this will come as 15 henries. So L is equal to 15 henries. Okay. So L is equal to 15 henries is the equivalent inductance. Now he has asked you to find out the reactance when the voltage of frequency 7 kilohertz is applied. So reactance XL is given as 2 pi FL. Okay, and now here it is 2 into 3.14 into F he has given us 7 kilohertz. So 7 into 10 to the power of 3 and L is 15 henries. 15 henries. Okay. So this is nothing but 2 into 7 is 14, 14 into 15, 15 into. So if you calculate this, 15 into 7 into 3.14 into 2, okay, this will give you the answer as 660. 660, and because it is 10 raised to 3, it is 660 kilo ohms. Okay, 660 kilo ohms is the answer here. So here you have to know that he has asked about reactance, and reactance XL. Okay, reactance XL is equal to 2 pi FL. So XL is equal to 2 pi FL. So, okay, so pi value you can take it as 3.14 or 22 by 7. F is given as 7 kilohertz and L we had calculated as 15 henries. Okay, so if you substitute this all values, pi you can take either as 3.14 or you can take it as 22 by 7. Okay, so if you substitute all these values, you will get 660 kilo ohms as the answer. Clear? Now, students, we'll go to the next question, question number 111. It says that what is the energy stored in the magnetic field if the current in a coil has a constant inductance of L henries and which grows at a uniform rate? Okay. Now, if this is the case, then we can go and see the relation that energy in an inductor when electric current is flowing in an inductor, there is a energy stored in the magnetic field. Considering the pure inductorial, the instantaneous power which must be supplied to initiate the current in the inductor is given as P is equal to IV. Okay. Now P is equal to IV. Let the value of I be like that. V is given as L di by dt. Then P will be equal to L into I di by dt. So the energy input to build a final current I is given by the integral of, okay, so power should be integrated with respect to time. First, energy stored is equal to power is integrated with respect to time. Then if you substitute that value of power and if you integrate with respect to current, then it is Li into di, which will be your I square into L, and you, because it is integration, you will get half at the output. So it will be 1 upon 2 Li square. So energy stored in an inductor will be half, that is 1 upon 2 Li square. Okay, so that is the answer for this. So here we can see option B is Li square upon 2. So that will be the answer for this question 111. Okay, then we'll go to the next question. Find the average current in an inductor if the total current in the inductor is 26 amperes. Okay, 26 amperes. Okay, now average current is given as, okay, average current is given as I by 2. Okay, average current is given as I by 2. If the total current is 26, then it is 26 by 2, that is equal to 13 amperes. So average current is equal to 13 amperes. So here option C will be the right answer. Okay, option C will be the right answer. Then we'll go to the next question, question number 113. Calculate the power in an inductive circuit if the inductance is 10 henries and the current flowing in the inductor is 2 ampere in 4 seconds. Okay. Now, whenever you see an expression for power, if you see an expression for power, it is L I square upon 2T. This is the expression for power. Okay. Substituting the values. Okay. So we have L as 10 henries into I is 2 amperes. So it is 2 square upon 2 and time is 4 seconds. Okay. So then P will be equal to 10 into 4 upon 8, which is equal to 40 upon 8, which is equal to 5 watts, which is equal to 5 watts. So power is equal to 5 watts is the answer. So option C will be the answer over here. That is 5 watts. Then we'll go to the next question. Question number 114. Calculate the value of stored energy in an inductor if the value of inductance is 20 Henry and 4 ampere of current flows through it. Okay. So he has asked to calculate the value of stored energy. Now, energy is given as Li square upon 2. Okay. Li square upon 2. Now, from the above statement, L is 20 Henry. Okay. I is 4 ampere. So it is 4 square and upon 2. Okay. So this is nothing but 20 into 16. 16 upon 2. So this is nothing but 320 upon 2. This is nothing but 160 joules. Okay, so energy stored is equal to 160 joules. So option D will be the right answer over here, 160 joules. Then we'll go to the next question, question number 115. Calculate the EMF induced in an inductor if the inductance is 10 Henry and the current is 2 ampere in 4 seconds. Okay. So he has asked to calculate the EMF induced. Okay. Now EMF is given as EMF will be given as L di by dt. Okay. Di by dt. Now here, so substituting the values, okay, in this we get, so L is equal to 10 Henry multiplied by di by dt is 2 ampere in 4 seconds. Okay. So if you do this, 2 ones are 2, 2 twos are 4, 2 1, 2 2 5s are 10. This is nothing but 5 volt. So EMF is equal to 5 volts. Clear? So here answer D will be the right answer. EMF is equal to 5 volt. Then we'll go to the next question. Question number 116. Calculate the current in an inductor if the energy stored is 160 joules and the inductance is 20 henries. So here he has given energy is equal to 160 joules and inductance L is equal to 20 henries. Clear? Now we know from the formula that energy is equal to L I square by 2. Okay. Now here you have got the value of E and value of L. Okay. So he has asked to calculate the current. Now in this formula, if you see, if you take current, I square is equal to E into 2 upon L. Okay. So E into 2 upon L. So you can take I square is equal to E is how much? 160 into 2 upon L is how much? 20. Okay. So this 0 goes, this 0 goes, this 2 goes, this 2 goes. It is 16. That means I is equal to under root 16. That means I is equal to 4 amperes. Okay. So here the answer will be D, 4 amperes. Right. Then we'll go to the next question. Question number 117. Find the time taken for the current in an inductor to change to 2 ampere from 0 ampere if the power in the inductor is 5 watt and the value of inductance is 10 henries. Clear? Now here if you see the inductor power, so power is given as 5 watts, inductance is given as 10 Henry. Okay. Now we know that power is equal to L I square upon 2T. Li square upon 2T. Okay. Substituting these values of L, I, and 2T. Okay, so I, we know that it is 2 amperes. So if you want to find out the time taken, then this formula will be rearranged as T is equal to L I square upon 2P. Okay, so here if you substitute the values, L is 10 Henry, I square is 2 ampere, so 2 raised to square upon 2 into power is 5s. Okay, so this is nothing but 10 into 4 upon 2 into 5. So this is nothing but 40 upon 10, which is nothing but 4 seconds. So answer should be 4 seconds here. So answer option D will be the right answer. That is 4 seconds. Clear? Then we'll go to the next question. Question number 118. Energy stored in 2000 millifarad capacitor charged to a potential difference of 10 volts is how much? Okay, so here we are having energy stored in capacitor. So capacitor value is given as C is equal to 2000 millifarad. Okay, 2000 millifarad. That means this is equal to 2000 into 10 to the power of minus 3 farad. Clear? Then we have potential difference of 10 volts. That is V is equal to 10 volt. Okay. Now from the expression, we know that the energy stored, okay, energy stored in a capacitor, okay, energy stored in a capacitor is equal to CV square upon 2. So this is nothing but C is how much? 2000 into 10 to the power of minus 3 into V square. V square is 10 into 10, okay, upon 2, which is nothing but, so 10 into 10 will go as 100. So this is nothing but 200,000 into, this is 10 raised to 2, 10 raised to minus 1, okay, upon 2. So this is nothing but 1000 into 10 raised to minus 1, and this is nothing but 100 joules. This is nothing but 100 joules. So option A will be the right answer over here, 100 joules. Clear? Then we'll go to the next question. Question number 119. When do we get maximum energy from a set of capacitors? Okay. Now, our capacitors, we know when they are connected in parallel, the concept of adding is C equivalent is equal to C1 plus C2 plus C3. Okay. That means we get maximum energy when the capacitors are connected in parallel, because combination of connection for capacitors is opposite of the combination of connection of resistors and inductors. So we get maximum energy when capacitors are connected in parallel. Okay, so here option A will be the right answer. We get maximum energy from a set of capacitors when they are connected in parallel. Okay, then we'll go to the next question. Question number 120. If the charge stored in a capacitor is 4 coulomb and the value of capacitance is 2 farad, calculate its energy stored. Okay, so a charge stored is 2 coulomb, and then you are having value of capacitance as 2F. So charge stored, that means Q is equal to, okay, charge stored in a capacitor is 4 coulomb. Sorry, and the value of capacitance is 2 farad. Okay, then calculate the energy stored. Now we know that the energy stored, okay, the value of energy stored can be given as Q square upon 2C. Q square upon 2C. So here Q square means 4 square, 4 square upon 2C means 2 into 2. So this is nothing but 16 upon 4. This is nothing but 4. joules. So energy is equal to 4 joules. So here the option B will be the right answer. That is 4 joules. 4 joules will be the answer for this problem. Okay. So here students have taken another 20 questions on BEEE basics of inductor, capacitors, energy storing and combination circuits. Okay. I will take another 20 questions in my next video on the next topic for this subject. Thank you very much.